So today we are going to talk about parametric equations. And parametric equations, they may be a new idea. Some of you may have seen this in physics. I'm not. They sound familiar?
No.
Okay,
Yes, they do.
all right, well then they'll be new, no worries.
Last year.
Okay, so first up, there's a couple of ways you can look at parametric equations. First thing, parametric equations comes from the word parameter. And I'm going to give what at first will seem like a not very useful definition of a parameter. And that definition is that a parameter is invisible. That seems like, that's not really a definition, it's just sort of a word that helps describe them. What do I mean by a parameter is invisible? Well, I'm contrasting a parameter with a dimension, which I suddenly can't spell. But the dimension, let's see if you guys have some idea what I mean. What are the dimensions on your average Cartesian graph?
X, Y.
X and Y, yeah. And you can see X and Y, these are stand-ins for length and width. Dimensions of length and width. Okay. See, Lauren? Good luck, you better win. Okay, so these are dimensions are X and Y. All right, and you can see them, right?
Yeah.
Okay, but we can also have parameters, and these are things in the background that can control the graph. They can affect the graph. They can change the shape of a graph, but you don't automatically see them. You only see the result of them. One quick example. You might have heard in physics that everything that flies through the air follows a parabola. If you watch me toss something, that was a parabolic path. You can see the parabolic path. But where this eraser is on a parabolic path depends on time. Do you see time?
No.
No, you just kind of see the parabola, and you see the eraser moving. And I could graph a bunch of little dots showing the flight of the eraser, right?
Yeah.
But there's no t-axis here. There's an x-axis for length, a y-axis for height. There's no t-axis for time, even though if something is moving in a parabola, time is pretty important, right? Does that idea make kind of sense?
Yes.
And time is probably the most common parameter in the background, but it can be anything. It can be temperature, pressure, in physics and chemistry. It can be all sorts of crazy things. So dimensions are visible. We can see X and Y. We can't see T as a parameter. Now, believe it or not, this is still a vector lesson. So what does this have to do with vectors? Okay, I'm going to give you one of my definitions that work, but is not a formal math definition. You won't find this in a textbook, and if you remember this into college and you say it to your college professor, he will laugh at you and tell you all the ways in which it's probably wrong, but it will work for this lesson and for many lessons after it. So are you ready for one of my slightly weird definitions that will work?
Yes.
Okay, all right. Think of what we're going to do is we're going to combine a point and a vector. Which is weird, because I kept saying vectors are independent of location. They can be anywhere, right? But what if they weren't? What if they weren't? So what we're going to do is we are going to, I'm going to go right to an example. We are going to find the parametric equations of a line passing through, and this is the exact example I previewed with Lauren earlier, passing through a point, I'm going to say 2, 3, and parallel to a vector, and that vector is going to be -1, 5. We're going to combine a point, which is location, with a vector, which is not, which is direction and magnitude. What does this look like? First off, I said find the parametric equations. I haven't even told you how to do this. Okay? There's a lot going on here I haven't covered yet. Let's break this down a little bit. Let's start simple. The point 2, 3, is that hard to find?
No.
That's not bad to figure out. Okay, so let's take a point 2, 3, Double check me, because every once in a while I mix up my x and y too, and my positive and negative. Is that correct?
Yep. Yeah.
Awesome. Now I'm going to take a vector. Okay, so I'm looking for the parametric equations of a line passing through 2, 3 and negative 1, 5. 2, 3 is a location, negative 1, 5 is a vector. Here's what that means. Follow this vector from this point. It's the first thing we're going to do. Follow this vector from this point. Pretend this vector has to be here. What would that look like? Any idea? What do you think, Bruno?
You go down just 1 point. So
Remember, oh, you're thinking like slope.
Oh, yeah.
And slope is rise over run. Slope is not a bad way to think of vectors, but if you think of a vector as slope, which is allowed, a vector would be kind of like run, rise. Also, slope goes on forever in both directions, and vectors don't. It's okay. What are you thinking?
Well, he's not right. He's right about slope, so if you just go down 1 and right to the 5, you can draw an arrow.
Well, down 1 though. Okay, Guillermo looks like he disagrees. What are you thinking?
It's 1 to the left, 5 up.
1 to the left, 5 up. Remember, a vector is horizontal, vertical.
Damn.
Okay, so you're thinking rise over run. You're remembering slope, but when you apply that to a vector, the horizontal comes first, then the vertical. So from here, I would go 1 to the left and 1, 2, 3, 4, 5 up, correct? Okay, so if I combined the idea of a location with the idea of a vector. Okay, all right. What if I did it again? You can't stop me from doing it again.
Like if you added another vector?
What if I add another vector to it? Yeah. Ben, what's your thought on that?
My name is not Ben.
Will, what's your thought on that? Will, what's your thought on your name? Sorry.
Would you start the next vector from the end of the first vector you drew?
I absolutely could. I could start the next vector from the end of the first vector and go over 1 again. 1, 2, 3, 4, 5. Is this starting to look kind of like a line?
Yeah.
Yes.
Okay.
It's a ray.
It's I got to be picky here for a minute. Rays go on forever by definition, and even though this looks like a ray, vectors are supposed to stop. Vectors have a set magnitude. Rays have an infinite magnitude. So it looks like a ray. I know it's hard because in geometry you were taught to draw a ray this way, right? But this vector stops here, and then this other vector stops here. What if I went the other way? What if I wanted to follow an opposite vector from that point? What would I do, Sarah?
Go to the right 1, go down 5.
Go to the right 1 and go down 1, 2, 3, 4, 5. That would look something like that, right?
Yeah.
Okay, so this is looking like a line. Now the problem is I'm breaking a lot of the rules of vectors. Because a unique vector has 1 direction and 1 magnitude. Okay? So adding this vector to this point would just really describe this vector sort of anchored here. This is sort of new crazy stuff that we're adding to it. So let's see if there's a way to describe that. Now mathematically this isn't quite what's going on, but I'm going to say that what we're doing is we're adding a point. This is the weird definition I mentioned. We're going to add this point, take this point, and we're going to add a vector to it. So this is kind of a crazy way to describe just this first vector. Okay? If I start at this point and I add this vector, I wind up right there. Does that make sense? How would I start at this point and get way up here? Will.
Start at 2, 3.
Start at 2, 3. How would I describe starting here and going up to here?
Would it be negative 2, 10?
As a vector, we could do that. Guillermo?
2.3, and like the point plus 2 vector. Vector.
Plus
2. Yeah.
Oh, okay, that's an interesting idea. Put a 2 there.
Yes.
And is this the same thing as you were saying?
Yes.
Because I can distribute this scalar.
Yeah.
So I can make this negative 2, 10, right?
Mm-hmm.
Okay. not Guillermo, but somebody else, use what Guillermo did and tell me how I would get from here to here, adding a point to this vector. Sarah.
You would do 2, 3, minus 2, negative, minus 2.
We only went down 1 here, sweetie.
Oh, I was gonna say, oh,
It's okay, you're right except for the 2 part.
yeah.
Okay, just 2, 3 minus this vector, right? Okay.
Wait, where's the 2?
Okay, the
Oh, wait, no, I see.
all right, this 2 was only here because we went, as Will put it, 2 to the left and 10 up. So we had to double this vector. If we're only going down 5 over 1, we don't need the 2.
Yeah.
Okay? So it looks like this is the sort of crazy part that I'm adding to it, where you take a point, you add a vector to a point, you wind up somewhere. Okay? What were the directions on this problem we're trying to solve, though? What did this say?
Parametric equations.
Okay, of a line. Is this an entire line?
No.
No, lines go on forever. How are we going to handle that idea?
Turn it into a line. Make it go on.
Make it go on forever?
Yeah.
We're just all going to agree that it goes on forever and then, walk away.
Can you elaborate your question?
Okay, if just this idea, I said, let's start at a point, and let's add a single vector to that point. That only covers from here to here. And then it stops, because vectors have a finite magnitude. Does that make sense?
Yeah.
Okay, and then this covers the idea of starting at this point and going twice that far, going up to here. But it's still not going on forever. Okay? Here's where I'm going to introduce the idea of a parameter, something invisible working in the background that turns this idea into an infinite line. I'm going to say, here's the point 2, 3 plus t. T is the most commonly used letter for parameters. T times the vector negative 1, 5. So when t is equal to 1, I'm saying start here, go up to here. When t is equal to 2, I'm saying start here, go up to here. When t is equal to negative 1, that means start here, go down to here.
Oh.
Is there any value that t can't cover? I mean, if t can be anything, would that allow me to pick a point anywhere on this line?
Yeah.
Yeah, and it'll keep me on this line too. This vector operates like a backward slope. It's run comma rise instead of rise over run. Okay? So this looks kind of like we're getting somewhere, and t is my parameter. T is my parameter. Let's look at our directions again. Find the parametric equations, plural, too. Wait, Bruno has a question.
Wait. Never mind.
Okay, so find the parametric equations. Is this more than one equation? This isn't even an equation. What is this?
It's a point.
It's kind of an idea. It's a point plus an infinite number of vectors. I don't even know what that means. We need to get 2 parametric equations out of this. Ben, do you have an idea?
We need to find a parametric equation for x and y.
Oh, somebody figured it out. Got clever there. Okay, we need 2 parametric equations. Tell me something about the 2 numbers I just highlighted. They have something in common. Sarah?
I want to roll.
Yes. Not the line. Guillermo?
They are in the x-axis. I mean, you moved in the x-axis.
You move in the x-axis direction. You move horizontally.
Oh.
They both mean, he was
I was about
going
to
to give
say-
me that word.
I was about to say they both move horizontally.
I have no doubt. Right. This remembers a point. This represents 2 units out on the x-axis, and this represents moving left horizontally. Okay? So with that in mind, now tell me something about these 2 points.
They both.
Say it, say it, say
They
it.
both move vertically.
They both move vertically. Well, this is you find this by going 3 up, then you move 5 up and down as t changes. All right, so now I'm going to take Ben's advice and split this up. I'm going to say that all my x's equal 2, because that's where we started, right? We started with an x value of 2, plus t times negative 1.
It's negative 1t.
Yeah, or even just
Negative t.
x. How about x equals 2 minus t? Is that an okay way to write it? Is my algebra okay there?
Yes.
Yeah, that would work.
Okay, and this takes care of all that's going on horizontally. And then I'm going to say y equals 3 plus t. Forgot to write the 3 part. Other than that, I'm doing great. Y equals 3 plus t times 5, which I could write as y equals 3 plus 5t. And these are two parametric equations that describe this line. Here are two parametric equations that describe this line. So let's pretend t is time. And there's a particle, there's a point, there's something floating out there, and it's described by these two equations. When t is equal to 0, when t is 0, x will equal 2 minus 0. What's that?
-2.
2 minus 0 is what?
-2.
2 minus 0 is positive 2, man.
Oh.
All right. Okay.
Oh no.
So 2 minus 0 is 2, not a trick question. Give you a second chance here. What is y equals 3 plus 5 times 0?
Okay. Voted in front.
All right. Guillermo, help him out here. 3 plus 5 times 0? 3. Okay. So when t is 0, you're sitting here at this point 2, 3.
Yeah.
When t is 1, 2 minus 1 is 1. 3 plus 5 times 1 is 8. You're right here. So when t is 1, it's like you followed the vector one length. When you plug in 2 for t, I guarantee you'll wind up here. Okay? Did you guys know your calculator has a parametric mode?
What?
Yeah.
We won't talk about that today, but of course you did. Parametric mode will let you graph things, and you can watch a dot move as you change t.
Bro, that's
It is kind of cool. We'll get to that a little later. That will not be today. So, if you have to find the parametric equations of a line passing through a point and parallel to a vector, you can write it like this, and then split up the horizontal and the vertical parts separately, and write your two parametric equations. Hang on for one sec. All right. Now, let's see if we can apply that to maybe an example or two. Write a vector equation describing a line passing through a point and parallel to a vector. Does this look familiar? It's frighteningly like what we did. We could graph it, but one way to think of it, and again, this is mathematically a little bit weird. It's like the math grammar of it is weird. But let's think of it as a point plus a vector. It's one way to say we're going to start at this point and add this vector. But we're going to add multiples of this vector, and that's where the parameter t comes in. From this point, we want to be able to follow this vector maybe once, maybe twice, maybe -5 times. That's where this parameter comes in. Okay? Does that idea make sense?
Yes.
Okay, maybe?
Yeah.
So if we write this out a step, we're going to start at 1, 4 plus t times the vector 3, -2. All right, now you guys, somebody, break this down for me. What are the horizontal parts? Yes, sir.
1 and 3.
Okay. 1 plus, can't just say the 3, you got to add in
3t.
1 plus 3t. All right.
Okay.
And now somebody break down the vertical parts for me. All right, Sarah.
4 minus 2t.
4 minus 2t. You guys are getting good at this game. Okay, so we can keep the, yes, sir.
There's a little something here. Could we also say 2 minus t? So why?
You can describe different parametric lines differently, but no, you're trying to just divide everything by 2?
Yeah.
No, because that'd be equal to 1/2 y. That would not give
Oh
you,
my god.
you can't just change one side of an equation, like the algebra rules are still true.
Oh, I thought that.
But you're on to one, your idea is not bad, because this is not the only way to parametricize this line. It's an actual verb. But this is not the only way to get a parametric equation for this line. We could pick a different point on this line and a longer or shorter vector as long as it was parallel. So there are multiple ways to make parametric equations for the same line. That's not one of them, sorry. Okay. Any questions on these steps? And if you wanted to graph it and draw some vectors, you would see how this would make a line going on forever in both directions. Let's see what the next example looks like. Find the parametric equations for a line parallel to vector q and passing through the point at -2, -4, then make a table of values and graph the line. Okay, this will get to something important about parametric graphs that I haven't mentioned yet. Let's get ready to graph this thing. No idea what points we're going to need. Okay, so first thing we need to do is set up our point plus t times a vector. Okay, somebody tell me the horizontal ones. Guillermo.
-2 plus 6t.
-2 plus 6t. It's almost too easy. Will, was your hand up for the last one?
I don't know, maybe.
Maybe. Can you handle the vertical?
That's a challenge.
All right.
Alright, y is equal to -4 minus 3.
Excellent. Okay, Bruno, you're looking enthusiastic, sir.
Yeah.
Okay, let's have you start the table. Okay. Here's the deal with the table for a parametric graph. We're only graphing x and y. Here's what I meant about visible and invisible. We're only graphing x and y, but my table is going to have t, x and y in it. We're only going to see these points. But we're going to figure out these points based on the t values. It's a little bit of a weird idea. Mia looks doubtful. I don't think she trusts this process at all. Hey Mia,
Yeah.
when t is 0, tell me what x and y are equal to.
X is equal to -2,
Yep,
and y is equal to -4.
cool. Makes sense. If you multiply your vector times 0, it goes away, and you should be sitting right at your starting point. Does that make a certain sense?
Yeah.
Okay.
Capiche.
Spencer,
Yes.
t is 1. Tell me what x and y is. If
X
t is 1,
would be 4,
double check that in my own head. Yes.
and Y would be -7.
-7. Okay. Let's start graphing these points. So when t is 0, I'm at the point -2, -4. Did I graph that correctly?
Yes.
Awesome. And then from that point, and then when t is 1, I'm at the point 4, -7. Is that correct?
Capiche.
If I put in a 2, I'm going off this graph, so I'm going to put in a -1.
Nice.
Okay, Bruno. T is -1. What is x?
X is going to be, so it's going to be -2 plus -6.
Which gets me to
And I don't have my calculator right now, so it's hard for me to do it in my head.
-8.
Yes.
Okay, somebody
Oh.
helped you out there. That will be -8. Okay, and when t is -1, what will y be? Somebody want to help me with that, Sarah?
-1.
No, you're right. Okay, cool. Yes. So when t is equal to -1, do these points look like they're on a line?
Yeah.
Okay, now, if I added a little something to the directions, what if I said to graph over this domain of t? What if I said only graph that part? I'm changing the example now in the middle. Messing with your heads. What do you think that would mean?
You would only graph the values of t of when t equals -1, 0, -1 or 0.
Okay, but does this mean you're making an assumption that we're only counting the integers? Hey guys, t can be fractions. T can be decimals too. So we get to fill in. We do get to fill in. I don't trust myself to draw a straight line.
You can graph any values up to 1. You can graph any values
You got it.
down to -1.
Excellent. Does anyone remember a difference in graphing between, when you were just on a number line, between whether the equal sign was there or not? What was the difference? Do you remember something? Yes, sir.
Oh, wait, graphing or?
When you were graphing on a number line, how you treated less than and greater than separate from equal to. Guillermo, what do you remember?
Shading.
You can put the t with minus equal. It can
Okay,
be
right, yeah.
1, but with the minus just, it cannot be 1.
Right, but how do I show that on the graph?
With an open circle.
With an open circle. Do you guys remember that idea?
Wait.
Okay, so when t is equal to 1, that was at the 4, -7, correct?
Yes.
Okay, so I can do, see how I'm opening up the circle there?
Ah.
And this tells me I can get really, really close to that 1, but I'm not allowed to fill it in. Does that make sense?
Oh, I did not know that.
No, that's what that means. So, oh, there's one other thing. Parametric graphs have a direction. And when you graph something parametrically, you're supposed to put an arrow on it to say you know what that direction is, okay? And that direction is always in the direction of increasing t. Okay, it's not in the direction of increasing slope of the line. It's not as the x or y values get bigger. This is thought to be moving in the direction as t increases. So when t is -1, we're here, correct?
Yes.
And then when t is 0, we're here, correct?
Yes.
And when t is 1, we're here?
Yes.
Yeah.
Okay,
Alright.
then this parametric equation has motion in this direction, and you have to put at least one arrow on it somewhere to tell me that you know that.
Very cool.
It's kind of cool. Because in real life, we only use, like, if I'm doing a parabola to model this thing's motion, okay? And I don't catch it, it's even more embarrassing. I'm using a parabola to describe that, okay? Now, when we graph parabolas in math, we talk about how they go down to -infinity, right? But in real life, this didn't start -infinity feet below the floor. And it doesn't keep falling forever. And in real life, time tells us when the eraser passes through each point in the parabola. So really, if you're going to describe something in the real world, it usually has a starting point, it usually has an end point, and you can usually indicate in which direction you're going as time passes. So parametric equations are actually a lot more useful than the kind of graphs you've been doing up to this point. Any questions on this one before I wander off?
Sure.
Okay, we made a table. It's got a direction. Awesome.
It's pretty good.
It's kind of cool. Okay. Oh, this is interesting. Okay. Write the parametric equations. This is something we haven't done yet. Of y equals -4x plus 7.
Ooh. I have an idea.
You have an idea? What do you think it is?
Could we make y equals 0 and kind of figure out?
Close. Close. What do you think?
Will we solve for x and y?
Exactly backwards. We're going to do that in a minute for something else.
Okay.
This is dirt simple and easy to forget. Guillermo, what do you think? Did you look ahead?
We can do that y equals t.
We could do that. I usually do the opposite, but we can do that. I usually do x equals t. Okay, this is super complicated for those who aren't following what Guillermo said. Are you ready?
Oh,
You guys ready? Okay. All this says is write parametric equations for this. I'm going to make x equal to t, and then y. If x and t are the same, what can I write there?
T.
T. Seriously, it's not complicated. I was lying. Boom, you're done.
What?
It's actually that simple.
But
Make x equal to t. If you have y by itself, make x equal to t, and then if x and t are the same, you can put a t there, and boom, these are parametric equations.
Can that be on the test?
Wouldn't that be nice? This is not the only way to do it. I could make x equal to t plus 1, and then I'd have to plug t plus 1 in. It would get more complicated. But this is the simplest way to take a line and turn it into a parametric equation, a set of parametric equations for a line. It really is that simple. We'll talk about why this is more interesting a little later, but for now, that's the simplest way to do it. Yes?
Why would you set x equal to t plus 1?
I wouldn't. Actually, I honestly wouldn't. If you're trying to model something in real life and your parameter is time, what if one of the things you're measuring the time of started a second later or an hour later? then you might parametricize things differently. This can get really complicated really quickly in real life.
Okay.
But if the instructions are just make parametric equations, oh, please do it this simply.
Okay.
Yeah.
Pick one of the letters, make it equal to t, plug it in for the other one, you're done.
Okay.
Okay, does that make sense?
Yes.
But yes, in real life, there's so many different ways you can do this. Any questions on this?
Okay.
All right, we'll talk later.
It's so easy that I can't call.
I know, it's the first thing. Kids forget that on the test because it's so easy. They can't believe it. It's embarrassing, actually. Don't be that kid. Write an equation. This is a slightly more difficult, and it's similar to what some of you guys were saying. Spencer, you had an idea like this. Write an equation in slope-intercept form of the line whose parametric equations are x equals -5 plus 4t
Wow.
and y equals 2 minus 3t.
Okay.
All right, this is slightly more annoying. Conceptually, it's not much harder than the other thing we did. But
Oh, I have it.
tell me something about slope-intercept form.
Y equals mx.
Y equals mx plus b. Okay, which variable is by itself in slope-intercept form?
The
Y.
The y. Okay. So if you want an answer that has y by itself, which we do, because they said slope-intercept form, then there's a set way to do this that usually works out with the fewest number of steps. Okay?
Yeah.
And that method would be solve for t in the x equation. Start with the x equation and get t by itself. That's step one. See where this is going in a minute, I hope.
Whoa.
So for example, add 5 to both sides of this equation. Did I do that correctly?
Yeah.
Yes.
Okay.
Equal 5/4, right?
Slow down, cowboy. I'm gonna write it a little differently for what I hope looks a little more clear. Divide both sides by 4, switch the sides. T is equal to the entire quantity x plus 5 over 4. Is that correct? Any flaw in my algebra?
No.
Okay, double check. I do make simple mistakes. Now I'm going to take this whole thing and I'm going to substitute it in for that t.
Oh.
And this gives me y equals 2 minus 3 times x plus 5 over 4. Now that's not super pretty, but is y by itself?
Yes.
Okay, yes, so if you're told to put parametric lines into slope-intercept form, which is a fairly common instruction in a chapter like this, take the x equation, solve it for t, and substitute that back into your y parametric equation, and you've got y by itself. You are now just a few algebra steps away from having slope-intercept form. They're not pretty algebra steps, I won't lie. We have to do something like, let's see, y equals 2 minus 3. Can I take that 4 in the denominator out if I want to?
Yes. Uh-oh.
I can do that.
You got him, Chief.
Okay. So then can I distribute that 3/4?
Yep.
I can.
Probably wouldn't be very pretty.
It's not going to be, but is it minus 15 over 4?
Yep.
Okay. I have two like terms here, the 2 and the negative 15/4. I have to add them. What's 2 as a, what's positive 2 as a fraction with 4 in the denominator?
8/4.
8/4. So I can,
Wouldn't it be y equals -3/4x minus 7/4?
is Ben correct?
Yes.
Yeah.
Minus 7/4.
That's what I said.
That took me a minute, okay. So the algebra wasn't pretty, but the steps aren't that bad, I hope, okay? Take the x parametric equation, solve it for t, substitute what you get back into the y parametric equation, and to get from there to slope-intercept form, a little bit of algebra. Some of you may, I went through that algebra a little quick. If you have questions on that, ask me later, but conceptually, can you handle that?
Sure.
Okay. Actually, that's where we're going to stop. There was a word problem. We're not going to have time to do well, but that you shouldn't need it for that tonight. We'll talk more over the next few days of the advantages for parametric equations, And we will come back to parametric equations later, okay?
Cool.
We will do, when we do conics, we will do parametric conics. When we do parabolas, we'll do parametric parabolas. But for now, we're just going to relate this to vectors, because remember, where do parametrics come from? They come from the idea that you add vectors to a point. That's the important part for this unit. All right, we'll stop recording there, and then I'll take questions, comments, concerns, or compliments.
You look nice today.
Thank you. I was hoping someone would say that.
How are you?